Good morning again. And this will be the last of the discussions on the formation history of the binaries that LIGO and Virgo are observing today. And yesterday we talked about two of the channels that might be responsible for the binary black holes that we see. Let me today mention a third one. The third one is dynamical formation. So remember, this is the matchmaking club of black holes. So the idea is we have to think not of the solar neighborhood, but of an environment with a high density of stars. So what's the density of stars in the solar neighborhood? Well, those of you who happen to know that the closest star, Alpha Centauri, is about 4 light years away, might from that conclude that, okay, 4 light years or 3 light years is about 1 parsec, so the closest star is about a parsec away. So you might guess that, okay, if the closest star is a parsec away, the density is on the order of 1 per cubic parsec. Those of you who happen to know that the universe or the galaxy has on the order of 10 to the 10th stars, and the galaxy is a pancake that's about order of 100 parsecs in height, at least as far as massive stars are concerned. That's roughly the thickness of the disk, and it's order of 10 kiloparsecs this way, right? Because we know we're about 8 kiloparsecs from the center of the galaxy. You might multiply 10 kiloparsecs, which is 10 to the 4 parsecs squared, by 100 parsecs. You get 10 to the 10 parsecs cubed. That's the volume of the galactic disk. And you put 10 to the 10 stars in it. And again, you conclude that the typical density is 1 per cubic parsec. So, okay, 1 per cubic parsec is not a ridiculous estimate. It's roughly right within an order of magnitude or so for most sort of typical galaxies out there in the universe, and it basically means there is no interaction with other stars unless you were born together with the other stars already in some kind of a binary or triple system. But there are exceptions, and there are a couple of places in the universe where the densities are much higher. At formation, you might have young stellar clusters due to the fact that you have a bunch of stars forming from the same molecular cloud, and those might therefore continue to interact. Frequently, they evaporate over time. If they're not dense enough, they disperse. But sometimes the clusters stick around, and in our galaxy there are something like 100 so-called globular clusters. So globular clusters are quite dense balls of stars. We're talking about something like between 100,000 and a million stars typically. And the central densities are, so let's say 10 to the 5, 10 to the 6 stars. And the central densities are quite high and perhaps reach something like 10 to the 5 to 10 to the 6 per cubic parsec. So now your densities are high enough that you might realistically have a chance of interacting with dynamically with other objects. What I mean by dynamical interaction, I simply mean you are flying close enough, your stars fly close enough to other objects that gravitational forces, Newtonian forces, are significant enough to change the trajectory. So you can think of these as the equivalent of electromagnetic Coulomb scatterings, right? You fly by and you can exchange energy and angular momentum with other stars. Similar things can happen in one other place, which is nuclear clusters. And we're again in general talking about similar densities. So there are two kinds of nuclear clusters, some that may not have a massive black hole, some that might. There are some differences between them. The ones that don't have a massive black hole, you can really treat them more or less as globular clusters. So I won't even talk about them separately. The ones that do have a massive black hole at the center, there are some interesting complications there, but Again, at lowest order, I'll mostly talk about globular clusters because it's a simpler picture. But if you think about, let's say, a massive black hole like the one in the center of our galaxy, Sagittarius A star, 4 million solar masses, has a something like, order of its own mass of stars within its so-called sphere of influence. That's actually the definition of the sphere of influence. And that means we're talking about, again, something like 4 million solar masses worth of stars within a sphere of influence extending roughly to 1 parsec. So again, we're talking about similar densities of order 10 to the 6 stars per cubic parsec. So let's focus on the globular clusters and think about what might happen there. Of course, you have a range of stellar masses, and some of the stars are relatively low mass main sequence stars for quite a long time, like our sun, and other stars are more massive, and they will, within a few million years, collapse and make black holes or neutron stars. The stars, however, are not uniformly distributed in the cluster, because massive things tend to mass segregate towards the center of the cluster. And you can think of mass segregation as a kind of energy equipartition. So it's actually, turns out, it's quite useful to think of globular clusters and these kinds of dynamical, self-gravitating dynamical systems with thermodynamic analogies. So you can, for example, imagine that you have some, over time, over many interactions, many scattering interactions, you end up with a kind of constant temperature inside your cluster, right? And remember that we can typically relate temperature to kinetic energy. So, kT is something like mv squared. And if the temperature is the same for all of your stars because you've successfully equipartitioned, that means mv squared is going to be the same for, more or less the same for all of your stars. But that means the stars with a high mass end up with a lower velocity, right? Velocity goes as 1 over the square root of the mass in this case. And what does it mean to have a low velocity in this dynamical system? Well, if I have a low velocity, I'd better be close to the center, right? It's impossible to just sit there with a low velocity if I'm going in an orbit at a 1 parsec radius with lots of stars inside this orbit, right? At that point, I'd better have, on average, a fairly high velocity in order to basically match the Keplerian velocity at that radius. But if I'm sitting smack in the center of the cluster, well, in principle, I can have a velocity of 0 and just sit there in place. So low velocities means that you're forced to sink down towards the center. So massive things go towards the center. What else happens? Well, once in a while, you will naturally form binaries, even if you didn't have any. First of all, you probably have some fraction of stars that are born in binaries, even in a globular cluster. But once in a while, you will form binaries simply because, let's say, 3 stars come close enough together that they have a 3-body interaction, and 2 of them stick behind and 1 gets exchanged, or gets ejected, I should say. And once you form binaries, one of 2 things can happen. Either that binary can be a soft binary or a hard binary. So what do I mean by soft and hard? Well, a soft binary is one whose orbital energy is less than the typical kinetic energy of a particle in that cluster. A hard binary is one whose orbital energy, which is more tightly bound, so its orbital energy, okay, up to a sign, is greater than the typical kinetic energy of the particle, of a typical particle in the cluster. Soft binaries tend to be dissociated over time. Something will fly by, will interact, the binary is not very tightly bound, and the binary just gets disrupted by this interaction. And then they reform in 3-body interactions. So soft binaries keep on forming and being split up. But hard binaries, and you will occasionally accidentally make a hard binary, they tend to get hardened over time. Because what happens is that you have a binary over here, and the third object flies by. And when I say it flies by, I mean it's a relatively strong encounter, so it comes within roughly the semi-major axis of this binary. And typically this third object, with this interloper, will leave with a little bit more energy than it came in with, which means that it takes energy out of the binary, which means the binary gets harder or tighter. So hard binaries get harder. Soft binaries are disrupted. And the boundary is roughly at energy of binary is of order typical mass of a star times the velocity dispersion squared. So if the hard binary gets harder over time, okay, that means you can gradually bring the hard binary closer and closer together, maybe eventually bring it towards merger. What else happens? Well, what else happens is that in these three-body encounters, and by the way, three-body encounters, you can just model them by doing a lot of numerical three-body experiments that are pretty cheap to do. So you can all go home and start your favorite little n-body calculator, or write your own for three objects. It's not that hard, and take a binary, toss another star at it, and ask what happens at the end of the encounter. And the encounters are rarely this pretty. I mean, what usually happens in practice is, this binary comes in, then for a while it sort of orbits around, all three of them are interacting, there is some god-awful mess, maybe for a while it looks like it's actually orbiting one of these stars, while this one is not doing much of anything. Then they come together again, and then eventually one of the three stars gets kicked out, and the other two, on average, end up being closer together. You also find, if you do these kinds of numerical experiments, that typically it's the lightest guy out of the three that are interacting in this way that gets kicked out. So you preferentially keep on putting heavier and heavier objects into your binaries by injecting the lightest guys. So you might end up with an exchange interaction where, for instance, if I initially had a binary composed of a 1 solar mass star, another 1 solar mass star, and a 5 solar mass black hole came by, it'll exchange in for the one of the 1 solar mass stars. Then a 10 solar mass black hole comes by and it exchanges for the other 1 solar mass star. So now you have a 5 solar mass black hole and a 10 solar mass black hole. Then at some point, a few more stars come by, and all they do, if they're light stars, is harden the binary. And then a 20 solar mass black hole comes by, and it exchanges in for the 5 solar mass black hole. And you end up with having tighter and tighter binaries composed of the heaviest black holes you have available to you in your cluster. Now, by how much do you actually harden the binary? Well, you can do this again. You can do lots of numerical experiments, or it turns out you can actually do a reasonably simple calculation, and you can convince yourself that on average, what happens is that you need, in order to significantly harden this binary by something like a factor of 2, you need to have a mass. If you already have a pretty heavy binary, you need to have a total mass in interlopers that's roughly of order the mass of the binary. So to harden by factor of 2 or factor of e, need total interloper mass that's of order total mass of binary. So if I already have a binary composed of 2 black holes that are, let's say, 30 solar masses each, and most of my interlopers are 1 solar mass stars, I might need something like 60 interactions, order of magnitude. Now, of course, things aren't quite that simple, because one of the things you can imagine happening is that sometimes, at some point, your rate of interactions must get pretty small, because as your binary gets tighter and tighter, we said that in order to have an interesting hardening interaction, and by that I mean something that really changes the energy, has an energy exchange, as opposed to just scattering the binary a little bit onto a different path, that's a so-called angular momentum exchange interaction, those are easier. So it's easier to move the binary to a different trajectory within the cluster. Those things are relatively easy to do, but to interact strongly enough that you actually take energy out of the binary requires you to come pretty close to roughly within the same major axis of the binary, right? So if I, have a star that's flying by here, it's not going to do much. And as my binary gets tighter and tighter, it becomes harder and harder to hit the small target. So you might think that your interaction rate at some point gets to be incredibly low. So let's try to do this calculation first in a way that I promise you will be incorrect, but we'll correct it later just to get an idea of how this thing works, right? So suppose at some point, let's say I do have this 30 plus 30 solar mass binary black hole, and I'm trying to get it to merge, to get close enough together through these dynamical hardening interactions so it can eventually merge within the edge of the universe once gravitational waves take over. Okay, for that I needed to be something like a quarter of an astronomical unit apart. So for my last few interactions, at least, I'm trying to hit a binary whose size is only about a quarter of an AU. Right? Imagine it's just a little bit wider than a quarter of an AU, so that's not good enough. It won't merge in the edge of the universe, so now I need to hit that binary. I need to make sure the rate of those interactions is high enough. Otherwise, if it takes me more than the edge of the universe to wait for the next interaction, well, this method won't work. It won't help me. So let's ask how rapidly these interactions happen. Well, consider this binary sitting here. I've got some target, so it has some scattering cross-section area sigma. Sorry, that was terrible because I used sigma for my velocity dispersion. Let's just call this A. I have some number density of other stars, n. I have the typical velocity of other stars relative to this one. Okay, that's sigma. So this tells me that if I multiply these things together, that tells me what the rate of interactions is, right? Because A is the target area, n is the density of objects that might potentially hit it. So if I ask myself, okay, if I have a target here and I have a bunch of, think about, again, about thermodynamics, a bunch of atoms flying around, I've got a target, I have the density of atoms in this room is n, the target area is A, and I want to know, okay, how many atoms are going to hit this per unit time. Okay, well, I consider a box, pick whatever arbitrary size of the box you want, some distance d out of the board. Okay, the number of objects in that box now is d times A, and the rate at which the objects within the box are going to hit this target is v divided by d, because that's the time it takes an object that's a distance d away, if it's moving at a velocity v, to reach the board. And so the d's cancel out, and you just end up with n times the area times the typical velocity. Does that make sense? Okay. So now let's put in some numbers. So let's say n is 10 to the 6 per cubic parsec. The area, okay, so we said that the area is going to be something like the, okay, if our binary is a quarter of an AU in radius, we need to get within that binary. So crudely, I'm going to say it's a 1/4 AU squared. And sigma, okay, what's the velocity dispersion of this cluster? Well, turns out it's about typically 10 kilometers per second. How do I know it's 10 kilometers per second? Well, actually, one way to do that is to just think of what would be the typical Keplerian orbital radius if you put in this kind of mass, 10 to the 5, 10 to the 6 solar masses within a, and you consider the typical radius. Okay, this is the central density is 10 to the 5, 10 to the 6 per parsec cube. So it might suggest that actually the size of the cluster is about a parsec. It's actually larger. The central density is that high, but the cluster is more dispersed. But you say, okay, I have 10 to the 5 solar masses or 10 to the 6 solar masses. I put in an object at a distance of a few parsecs from that. What is going to be its Keplerian velocity? That's a good estimate for the dispersion velocity in the cluster.
Why not use the virial theorem?
But it's exactly the same thing.
Okay,
Exactly. I mean, the virial theorem is basically, you know, when I say Keplerian velocity, right, you know, it naturally comes out that the kinetic energy is half the potential energy with the appropriate sign. Exactly. So this is, you know, the order of 10 kilometers per second. All right, so now, all right, this is slightly inconvenient because I have kilometers in one place and AU in another and parsecs in a third, but let's try to do this anyway. So remember that a parsec is about 2 times 10 to the 5 astronomical units, right? And that's just because a parsec by definition is a parallax second. So all you have to do is say, okay, if I have a triangle that's 1 AU on one side and whose angle opening onto that 1 AU is 1 arc second, then the long side of the triangle is going to be 1 parsec. So the ratio of a parsec or of an AU to a parsec is the same as the ratio of an arc second to 1 radian. So this is about, should we do this all? Yeah, I guess we should probably, let's do this all in AU for simplicity. Okay, so this thing is going to be 10 to the 6 times 2 times 10 to the 5 to the minus 3. And this is AU minus 3. Okay, this thing right here is order of 0.1 AU squared. This thing right here, okay, so, and 10 kilometers per second. So one simple thing to remember is actually that kilometers per second and parsecs per year have an interesting conversion. This is just for general reference. But if you think about it for a moment, 1 parsec is 3 light years, give or take. 3 light years is 3 times, okay, the speed of light is 3 times 10 to the 5 kilometers per second, and a year is 3 times 10 to the 7 seconds per year. So now we have 3 times 3 times 3 is 30 times 10 to the 12. So this is 3 times 10 to the 13 kilometers. That's 1 parsec. Do I actually want to do it this way? Let me just think for a moment. Maybe I don't want to do it this way. Maybe, hold on. No, that's fine. Okay. So, all right. So, 1 parsec per year, therefore. Sorry, I'm going to go back and divide by years, which is why I realized that I was doing something silly. But 1 parsec per year is, therefore, 3 light years per year, if you wish. Right? Sorry, I realized I did a bit of extra algebra I didn't need to do. And so that is telling you that let me do this right, because I'm now embarrassing myself. Okay, sorry. Okay. Yes, this is exactly what I want to do. Okay. So this is okay. All right. We'll get there. We'll get there. I promise. Okay. So okay. So this is 3 light here. Okay. Hold on. This is being on the board is always tricky. I apologize. Okay. So we've got Sorry. Let me. Since I already wrote it this way, let me do it this way. I'm not going to try to be clever, and I'll just do this brute force. Okay. So a parsec is really 3 times 10 to the 13 kilometers. That means that a speed of 1 parsec per year is a speed of 3 times 10 to the 13 kilometers per year, which I can multiply by 1 year divided by 3 times 10 to the 7 seconds, and I immediately get 10 to the 6 kilometers per second. So 1 parsec per year is 10 to the 6 kilometers per second. That means 1 parsec per million years is 1 kilometer per second. And this is actually what I wanted to say. So a kilometer per second is a parsec per mega year. Okay, this is useful, for example, if you want to ask yourself, okay, how far, if I get my double neutron star system, gets, because of supernova kicks and so on, has a velocity on the sky of 300 kilometers per second, and it has a billion years between formation and merger, how far can it move away from its birth location within the galaxy? So if I use this conversion, I say, okay, well, it has a velocity of 300 kilometers per second, so that means it has a velocity of 300 parsecs per mega year. So in a giga year, it moves by 300 kiloparsecs. Okay, that's quite a bit. It means that if I didn't worry about the galactic potential, or it had enough velocity to escape from the galaxy, it would move very far outside of its host galaxy, and certainly within its host galaxy, it can basically take on a random location that's going to trace the galactic potential rather than tracing the burst sites. So we don't necessarily expect short gamma ray bursts for this reason to trace the location where the binaries are born in the galaxy. We expect them to trace more or less the potential of the galaxy. Did that make sense? Right. So just saying that this is a high that even 1 kilometer per second, or certainly 100 kilometers per second, is a high enough velocity that if you are willing to wait for a billion years, you can move to any location you please within your galaxy, or even if you can escape from the galaxy, you can end up somewhere in the intergalactic space, and possibly some hostless short gamma ray bursts are indeed the results of double neutron stars that got kicked out, that are merging after getting kicked out of their host galaxy. Okay, so apologies for the slight embarrassment over here, but what we ended up saying in the end is that 10 kilometers per second is going to be 10 parsecs per mega year, so 10 to the minus 5 parsecs per year. And of course, we now say, but we want to go back to AU, so we multiply by 5 times 10 to the minus 6 AU per parsec. Okay, now I really do have AUs everywhere except for this one over here. So now let's just try to take all of my variables here together. I end up with something that looks like 10 to the minus 10, 10 to the minus 11, 10 to the, okay, this gives me 10 to the minus 15, so that's now 10 to the minus 26. I multiply this by 10 to the 6, I get 10 to the minus 20. So I end up with a number like 10 to the minus 20 per year. And I say, the age of the universe is about 10 to the 10 years. If my interaction rate is 10 to the minus 20 per year, that means I have to wait for 10 to the 20 years to my next interaction, and I will never have that interaction. So great, I brought this binary at some point to maybe a distance of a few AU or a few tens of AU, and at that point I'm done. There are no more interactions to be had. I will never be able to bring the binary close enough together, because now it's longer than the age of the universe to the next interaction. I'll never be able to bring the binary close together for gravitational waves to take over. So why am I bothering talking about this channel if it clearly doesn't work? So I'll give you a hint. This was wrong. Does anybody have an idea why that was wrong? So let me ask the following question. Suppose I have this big ball of mass here, and it has also some size, right? It's a target. And I want to hit this target. So if I throw something really fast at this target, then this thing that's flying fast will just fly by and will, never be affected by the target. And if I don't aim it well enough to hit the target, tough luck. But suppose that I throw something pretty slowly. And it's a little bit, of course. I throw it actually towards Nelson instead of towards my target by mistake. But Nelson is light, and my target is very heavy. So what's going to happen? Well, gravity is going to happen, right? The path of my dart is going to be deflected by this very heavy target. And if the target is heavy enough and my object is moving slowly enough, it has enough time to accelerate the object, and the object will hit the target after all. That's called gravitational focusing. So in this case, your mass is acting just like any, other lens, right? Just like the lenses in eyeglasses are deflecting light here, and we talk about the focusing of light. Here we can talk about focusing by gravity. So because of this focusing by gravity, and the fact that our objects aren't moving all that quickly, 10 kilometers per second is not the speed of light, right? The speed of light is 3 times 10 to the 5 kilometers per second, so objects aren't moving all that quickly. You can get quite significant deflections. And so things which might otherwise not have hit the target will do so. So we can ask, okay, how close do you really need to toss things in order to be appreciably deflected? And the answer actually again goes back to virial theorem, which Nelson so nicely introduced, right? And it's a statement that, well, by the time, if I get to a point where my kinetic energy relative to the target is of order the potential energy due to the target, then I get a significant deflection that can basically bind me to the, essentially I get bound to the target and I will hit it. Whereas if I never get to that point, in other words, if my kinetic energy is always much larger than the potential energy relative to the target, well, my deflection is not going to be very appreciable and I will just keep flying on my merry way, right? I'll never get bound to the target. So you can think of it as a kind of binding. If you think of it that way, you will actually get an answer that's something like a factor of 2 off, but for our purposes it doesn't matter. So basically what we are saying is we don't need to actually aim to hit the target. We need to aim so that we have some impact parameter b, right, some nominal distance from the target if we kept going in a straight line and never quite hit the target. And our impact parameter must be such that gm over b is of order sigma squared. Because sigma is what our velocity relative to this target would, that's the velocity dispersed in the cluster, so that's roughly what our velocity relative to the target would have been if we didn't have any gravity, right? So if you think of, little m, I cancel little m's on both sides, but if you think of little m sigma squared over 2 as my kinetic energy, g big M, which is the mass of the binary, divided by the impact times little m divided by the impact parameter b is my potential energy. This just tells me, at what value of the impact parameter am I going to get bound, right? And this says, well, I'm actually going to end up being bound at a value of the impact parameter which is of order gm binary over sigma squared. And if you do this right, you find that your overall scattering cross-section, your area for the interaction, in fact, instead of looking like this is little a is the size of my binary, instead of looking like just little a squared, it looks like little a times gm binary over sigma squared. So you win by this ratio of gm binary over sigma squared relative to a. I'm sorry? No, so it's not, okay. So yeah, you might think that the scattering cross section is b squared. It's actually not quite b squared, because I really do want to come not just b. Okay, so the reason I still have an a in there is that okay, we can try to derive this more carefully, but it's basically I don't want to just be bound to the binary and sort of come somewhere close to it. I really want to come within the separation a. So if you write this down properly, you find that actually if I am in this gravitationally focused regime, I end up having a cross section for getting within a distance a that really scales as a times gm binary divided by sigma squared. So it's a times b in this case. That's my actual scattering cross section for getting within that separation a. I'm still sensitive to the value of a, right? The value of a still matters. And so I can ask, okay, but what kind of an enhancement is this? And well, if I consider this gm binary over sigma squared, all right? So gm binary, remember the mass of my binary in my favorite units of kilometers, let's say. The mass of the binary is, has 30 solar mass companions. One solar mass is 1.5 kilometers. That means the mass of the binary is about 100 kilometers. If I'm going to play it this way, then my sigma had better just be in dimensionless units. So in units of the speed of light, okay, if I'm talking about 10 kilometers per second, that's 3 parts in 10 to the 5 of the speed of light. So that squared gives me 10 to the minus 9 of the speed of light. So I'm dividing by that. So I end up with 100 kilometers times 10 to the 9 kilometers. So now I end up with 10 to the 11 kilometers, which, as you can see, is now significantly larger than an AU. An AU is only 10 to the 8 kilometers. So I'm winning by a factor of 10 to the third, which isn't quite enough, which suggests that I made a mistake somewhere. Because I'm now claiming that I only win by a factor of 10 to the third, and I think I should be actually winning by a higher factor. So what could I have done wrong? Just a moment. Sorry, not times 10 to the 9 kilometers, just times 10 to the 9. I apologize. 3 times 10 to the 5. No, that's right. Okay, so this definitely gives me an advantage, and I've screwed something up, and I will try to fix it later. I apologize. This is the problem of trying to do this on the board. But the short answer is that you do find, if you believe that or if I can manage to get the units to work out, you should find that your scattering rate gets high enough that you actually are able to have interactions going all the way to bringing you all the way to binary hardening. I was trying to calculate little b, and then I said that my ratio of little b to little a, which is the level of enhancement I'm having here, because my little a was about a quarter of an AU, and this is about 1,000 AU. I get a factor of 4 times 10 to the 3 enhancement, maybe 10 to the 4 enhancement. But if I get only a factor of 10 to the 4 enhancement in my cross-sectional area, that only decreases this or increases this by a factor of 10 to the 4, right? So it basically means, I have interactions a factor of 10,000 times more frequently, but I actually want them about a factor of 10 to the 10 times more frequently, so that's not enough. So I did make an arithmetical mistake somewhere, and I apologize for that. I will fix it, I promise. And if Nelson will tell me what the email list is for the people here, I can try to send an email, for example. I do apologize for that. Okay. Okay, with apologies for the arithmetical mistake, we hopefully, okay, you can hopefully trust me that if you have these 3-body interactions, you really can start significantly hardening the binary. Now, it's worth keeping in mind, and you can harden it all the way to the point where gravitational wave emission can take over and bring it to merger within the age of the universe. Now there are a couple of other complications. So one additional complication is that at some point you start ejecting the stars altogether, the interloper stars. Why do you eject the interloper stars? Well, this cluster, which has a velocity dispersion of 10 kilometers per second, is only going to have an escape velocity of about 50 kilometers per second. It isn't all that massive. It's not all that hard to escape from it. So if it has an escape velocity of only about 50 kilometers per second, you might ask yourself, well, what kind of a velocity will these stars end up with? Well, I already told you that I am how much energy the stars typically get, because I said that, if the total interloper mass is of order the mass of the binary is hardened by a factor of 2. So let's suppose, for the sake of argument, just to keep things simple so I don't have to worry about small masses and big masses, that actually my interloper has a mass, of the same order as the companion mass, or even of the same order as the binary's mass, just to get us kind of a right ballpark number, right? So in that case, if it's going to, that one interaction will significantly harden the binary, that means that the extra energy the interloper gets is going to be actually comparable to the binary's orbital energy. In other words, its velocity with which it is getting kicked out is of order the binary's orbital velocity. But if you ask yourself, what is the orbital velocity of two 30 solar mass black holes orbiting each other at a distance of a quarter of an astronomical unit, you find that it's hundreds of kilometers per second, right? And you know that because you know that the velocity of the Earth going around the sun at 1 AU is 30 kilometers per second. And the velocity goes as root m over the distance. So if I increase the mass by a factor of 60 and I decrease the distance by a factor of 4, I end up with something like a square root of 200 enhancement. So it ends up taking me from 30 kilometers per second to about 500 kilometers per second. So these binaries are orbiting each other at a velocity of 500 kilometers per second. That's the kind of kick that an interacting interloper is going to get. That's 10 times larger than the escape velocity from my globular cluster. So I start pretty quickly kicking out objects. Now, kicking out a few stars isn't going to create too much of a problem, but one of the problems is, remember, a lot of my interlopers are actually going to be other black holes, because these binaries are sitting deep in the center of the cluster, and I said that there is mass segregation, so other massive systems, massive objects like other black holes go to the center of the cluster. So I will waste a whole bunch of black holes, other black holes, in order to bring this binary close to merger. I will waste them in the sense that I will kick them out of the cluster. They won't have an opportunity to participate in future mergers. Another problem is, at some point, I might kick out the binary itself. I mean, if I'm kicking out an object here with a velocity of 500 kilometers per second, then of course, by just conservation of linear momentum, the rest of the binary has to move with a velocity in the opposite direction that's the same 500 kilometers per second, but prorated by the ratio of the mass of the interloper to the mass of the binary. And if the interloper is 1 solar mass and the binary has a mass of 60 solar masses, okay, fine. It's 500 kilometers per second divided by 60, and okay, that's 10 kilometers per second, and you don't have a problem. But if the interloper is a more massive 10 solar mass object, then we're back to 100 kilometers per second recoil kick that the binary gets, and the binary gets ejected from the cluster. And in fact, it's this recoil kick, the fact that you will at some point eject binaries from the cluster, that determines whether or not your cluster will be able to form merging binary black holes. So it turns out, for example, that this creates a threshold on the mass of the cluster and the size of the cluster, which equivalently tell you something about the velocity dispersion and the escape velocity. Those two things determine whether or not your cluster is actually going to be able to form massive black hole binaries, or whether you will end up through recoil kicks, ejecting those massive black hole binaries before they got tight enough to merge in the edge of the universe. Now, some massive black hole binaries, you might eject them from the cluster and they might still merge within the edge of the universe. So it doesn't mean that all the mergers have to happen inside the cluster. So in fact, people who've tried numerical simulations of this, like Carlos Rodriguez, have found that roughly half of the binaries end up merging outside the cluster after getting kicked. And that's actually important because it means that even if you did manage to localize somehow exactly where this binary has merged and pinpointed all the way down to the level of accuracy which was, allow you to resolve individual globular clusters, it wouldn't necessarily mean that you could be absolutely sure that, for instance, this binary did not come from a globular cluster from this dynamical channel just because it merged in a place in the galaxy where you don't see any globular clusters, right? It might have still gone to this channel and then gotten kicked out. And remember, we said if it's getting kicked out at a velocity of 100 kilometers per second, then in a billion years, it ends up being anywhere in the galaxy in some random location, nowhere near a globular cluster. But can we at least crudely estimate what the rate might be given all of these caveats? Well, we can at least estimate an upper limit on the rate through this channel. And the way you can estimate an upper limit is to say the following thing. We know observationally how common globular clusters are. There are about 100 globular clusters in our own galaxy. And that's not an insane number. It's reasonably typical. Elliptical galaxies have greater density of globular clusters. They may have 1,000 or even 10,000 globular clusters. But then elliptical galaxies are more rare. So we can take this number of 100 globular clusters per Milky Way galaxy, multiply this by the density of Milky Way-like galaxies, which is 1 per 100 cubic megaparsecs, and find that there is roughly 1 globular cluster per cubic megaparsec in the universe. Yes? Right. So in fact, right. So the giant ellipticals not only have them, they have them in greater abundance. Yeah. So a typical elliptical will have something like 10,000 globular clusters for a giant elliptical. Between let's say 1,000 and 10,000. But then giant ellipticals aren't all that common, right? You've got this Schechter function of galaxies, which basically says that at some point, for high enough masses, you have this almost exponential fall off in the space density of galaxies. So overall, that's actually within a factor of a few. This turns out to be a pretty good estimate for the total density of globular clusters in the universe. Yeah, so as far as we know, the vast majority of globular clusters are, something like 12 billion years old or somewhere around there, and that's true almost everywhere. We do see some exceptions. There is one globular cluster actually in the Milky Way whose name escapes me at the moment. I want to say Westerlund 1, but I don't think that's right. Which is only about 5 billion years old as far as we can tell. But yeah, the vast majority of them seem to be quite old. So let's assume that the globular clusters, have an age approaching the age of the universe. Globular clusters are actually a fascinating topic of its own, and people are, on the one hand, they're fantastic laboratories for stars because you might think that all the stars were born almost at the same time, and then you find that somehow they weren't because there are multiple main sequences and multiple different levels of chemical enrichment in globular clusters. Then you find, some other crazy things like very unusual elemental abundances, and anyway, you can exploring just understanding globular clusters is on its own a fascinating topic. But since we promised we would try to get at least an estimate, an upper limit on the contribution of this channel to the overall binary black hole merger rate, let's plow right ahead and notice the following, that we said, and I think we said this yesterday, that very crudely order of magnitude, something like 1/1000th of all stars actually end up making a black hole. So if you have a globular cluster with about 10 to the 6 solar masses worth of stars, it will end up with something like 1,000 black holes in it. And this is being fairly generous because some globular clusters aren't quite this massive, but 1,000 black holes per globular cluster. Now, let's say that all of our black holes end up merging in binaries in the globular cluster. Let's even imagine that they keep on being reused. So, and though I will argue that that's actually very implausible in a moment, but let's imagine that you keep on reusing them, and so if you merge two black holes, they make a black hole, the black hole sticks around, merges with another black hole, you never kick out any black holes. That means you get 999 mergers out of your 1,000 black holes. Okay, that's really an upper limit here. So if you get, that means in the history of each globular cluster, you can get 1,000 binary black hole mergers at most. Now, the age of the globular cluster we said was about 10 gigayears for round count. Now, many of the mergers might have actually happened very early in the history of the cluster, which means in the local universe, you might not have, because the globular clusters are old, just as you pointed out. In the local universe, you might not have a lot of mergers in that case. If all the mergers happened when the cluster was young, they would have happened long ago at high redshift. But let's imagine again, be favorable to ourselves. There's certainly no reason to think that 10 gigayears is a special time to merge. So let's imagine that the merger rate is uniform over 10 gigayears. So imagine that all of these black holes are merging uniformly over 10 gigayears. So that means my 1,000 mergers per globular cluster times divided by 10 to the 10 years and times one globular cluster per cubic megaparsec. And that gives me 10 to the minus 7 mergers per megaparsec cubed per year. And if I want to convert this into per gigaparsec cubed per year, because that's what the units that LIGO has quoted and that's what we measured everything else in, I remember that there are 10 to the 9 cubic megaparsecs in a gigaparsec, and so I get 100 per cubic gigaparsec per year. Now this number looks okay. It looks pretty consistent with the LIGO Virgo claimed rates, right? We said it was somewhere between 10 and 200 per cubic gigaparsec per year, and so you might say, yeah, okay, this could be a viable channel, could even be a dominant channel. But remember that we've taken some pretty impressive upper limits here. So the rate from this channel is actually more likely to be something like 5 or 10 per cubic gigaparsec per year, because, for example, a lot of your black holes will have been ejected from your cluster in the process of making these hard binaries. So you're depleting the black hole population, and also not every single black hole is going to merge. You will end up with some black holes even after 10 to the 10 years that are just sitting around in the cluster, and so this ends up being an upper limit, and the real rate is probably something like an order of magnitude lower, or maybe even a little bit more. Also, okay, although this is only a factor of 2, but it's worth mentioning because people have talked about whether or not you can reuse black holes, and what I mean by reusing is, can you merge two black holes together and then have that merger product participate in another merger? Doing that would be kind of cool for a variety of reasons. One is, by the way, that it would make it, since we talked about this earlier, it would make it harder to test the pair instability supernova hypothesis, right? So remember we said that we have this hypothesis that you should never end up with black holes weighing in between roughly 50 and roughly 130 solar masses. because things that would have made those black holes from single stellar evolution should have exploded in a pair instability supernova or reduced their mass through pulsational pair instabilities, avoiding a complete explosion. And so none of the companions in the merging binaries should be in that mass range, unless, of course, you can reuse the merger products of binary mergers, right? So as Alan pointed out, we do know of a 60 solar mass binary black hole. That's a merger product of GW 170817, or sorry, GW 150914. Let's say if we now say that that merger came from a globular cluster, which is perfectly plausible, and we say the black hole stuck around, okay, maybe in another billion years, it is going to merge with a 30 solar mass black hole, and now you have a 60 plus 30 merger, and lo and behold, one of your companions is actually in this pair instability supernova mass gap. So maybe we look at this and we say, oh, look, there is no mass gap there, but in fact, there is from single stellar evolution. It's just telling us that sometimes you can dynamically form more massive black holes. So why can't you do this? Well, the simple, okay, one of the possibilities, one of the arguments we already went through here, you might eject the entire binary and merge it out of the cluster. But then I said, okay, but actually probably half of your binaries do merge within the cluster. So maybe you do keep the black hole there. So one thing that we haven't talked about here are gravitational wave recoil kicks. I don't know if people have people discussed them in other lectures already. So when you get a binary to merge, your gravitational wave emission isn't actually completely symmetric. At any given time, gravitational waves are beamed, and it's true that over many orbits, you tend to average out that beaming. But that's only true if your sort of this part of the orbit and this part of the orbit are completely symmetrical. That'll be true if you have equal masses, always. But if you have unequal masses, then, and you actually have significant in-spiral going on, which you do in the last few cycles, you find that here I'm moving this way and my gravitational waves are actually preferentially beamed in this direction. Then, as I'm moving this way around the stable, my gravitational waves are preferentially beamed in this direction, except I'm a little bit closer because I've spiraled in, and my gravitational wave emission is a little bit stronger. So it doesn't quite cancel the waves I beamed in that direction. And so that means that as I'm spiraling in, and I sort of integrate over all of my orbits, I find that on average, in total, I've actually emitted a little bit more gravitational radiation in one direction than another. The direction is random, it's just a function of what exactly was the phase at the time I started plunging in, the phase along the orbit. But those kicks can be quite significant. Some 30 years ago, people, actually more than 30 years ago, I think 1981, Echeverria estimated what the kicks would be and found that the maximal kicks corresponded to a mass ratio of about 3 to 1, and you got kicks of about 170 or 180 kilometers per second, something in that ballpark, if you have a 3 to 1 mass ratio binary. But then people realized that things can get and even that, by the way, would be enough, 180 kilometers per second. Remember, the escape velocity is 50 kilometers per second in globular clusters. That's enough to kick you out already. But so if you have 3 to 1 mass ratios, you're in trouble. But you might say, well, if my mass ratios are always 1 to 1, then there is, or very close to 1 to 1, then there really is complete symmetry and there is no kick, so I'm okay. But keep in mind that actually things get much worse when you include the possibility of spins on your black holes. And the exact value of the kick depends on the magnitude of the spins and the orientation of the spins, but there are some so-called super kick configurations where if you have really high spins and the spins, if I remember correctly, are oriented in such a way that they're roughly in the binary's orbital plane but kind of pointing in opposite directions. So here's my, these two arms are my binary orbiting like this, and the kicks are pointing in this direction. You can get kicks of 4,000 or 5,000 kilometers per second. So that's going to eject you not just out of a globular cluster, that will eject you out of the most massive galaxies. Yes? So in this case, things get a little bit more tricky because in general, you don't necessarily, because your black holes may have evolved individually, not in a binary, or evolved in maybe in a wide binary but non-interacting binary, you don't necessarily strip off the envelope. And so if you don't strip off the envelope, my previous argument that says, oh, if you very quickly remove the envelope of the star, you don't have time initially, because the moment of inertia of the envelope is so much larger, just because the envelope is out here and the core is here. All the angular momentum is in the envelope. You don't have time for the star to take that angular momentum and pull it back in towards the core. So you've just removed all the angular momentum, you stripped it off the star, and you end up with something with this very small amount of angular momentum, hence a low spin. This doesn't necessarily work if you don't, this argument doesn't work if you don't have these kinds of interactions, because, okay, if I just have a single star sitting here, the star may have initially been born with some rotation. Therefore, it has some non-zero angular momentum. It maybe continues having this non-zero angular momentum, and it just at some point has a supernova explosion, and maybe you have almost complete fallback if you're forming a sufficiently massive black hole. So almost all of the none of the material is actually ejected into space, so you keep hold of all of your angular momentum in that case. A couple of caveats. One is if you have a single star and you have non-negligible metallicity, you have non-negligible winds, you will actually lose a fair bit of angular momentum through winds, and you will spin down your star. The second caveat is that during a supernova explosion, at least some people have argued that even if you have almost complete fallback, in the sense that you're not destroying any part of the core of your star, the envelope is very likely to be ejected anyway, because the envelope is so loosely bound, and so it doesn't take much to eject the envelope. So Elliott Quartard and his collaborators had some papers on this recently, for example. And okay, in that case, the question is whether or not for this pre-supernova star, how much of its actual angular momentum is in the core versus the envelope, and whether you really remove the envelope with its angular momentum or not. So the short answer is I don't know, but people have argued that maybe in this case you might have more significant spins, and if you do have more significant spins, you would expect them to be misaligned. You would expect the spin directions to be isotropic relative to the binary's orbit, because remember, you just take two black holes, whatever spins they have, and you bring them together to some complicated dynamical processes which don't care anything about the spins. The dynamics is happening on much larger spatial scales than the spatial scales in which the spins significantly curve space-time, and so that basically means the spin directions end up being completely random. And of course, one of the ways we can look for this then is to ask, do we see evidence in the observed population of merging binary black holes of an isotropic distribution of spin-orbit angles versus preferential alignment? The trouble is that's not so easy to do if the spins are typically all small, right? So if the spins are all very close to zero, you expect the thing you can measure well at the moment is this effective spin parameter, spin in the direction of the orbital angular momentum, and okay, if both spins are small, that's going to be close to zero, no matter whether the spins are aligned or misaligned with some isotropic distribution. If the spins are large, then you actually can say something, and in fact, we've written a paper, I guess about a year ago, with Will Farr and Cole Miller and a couple of other collaborators, which argued that, well, already from the first few LIGO observations, we can say that high spin magnitudes and preferential alignment are disfavored. Okay, that's kind of an obvious statement if you look at the data. We just try to quantify this a little bit more, what it means by being disfavored. But we said that already, if you believe that the spin distribution favors relatively high spins, there is already a few sigma confidence in favor of saying, in that case, probably you're pointing towards isotropically distributed spins rather than aligned spins, because aligned spins would mean you always should get a high effective spin, whereas isotropically distributed spins means sometimes you should get a spin that is, they can still be close to zero because, okay, either they cancel each other or they're both in the orbital plane and there is no net spin in the direction of the orbital angular momentum. But even that you can test, because you should say that, okay, but if the spins are high, even if they were isotropically distributed, then at some point you should also find a configuration where both spins point down. Sorry, when I say down, I mean orbital angular momentum points up and both spins point down, right? So that means you should have a significant negative value of chi effective. And if you see, for instance, that all of your chi effectives are either zero or have small positive values, then actually that should convince you that you're probably not going through this channel a lot of the time, because that would convince you that maybe there is some preferential alignment if things are, either zero or just slightly positive all the time, but that the spins are low, the spin magnitudes are low. So these are the kinds of things we will in principle be able to test with more detections. It's simply that the lower the spin magnitudes, the harder it is to infer information about the spins, because 0 plus or minus 0 is still very close to 0. Okay, so now what else do we want to say? Well, we want to say maybe a few words, now that we're getting to the end, about what the future might hold in terms of these observations. So I presented a few channels. One channel, by the way, I didn't discuss in detail, maybe I should just say spend 2 minutes on it, is that you can have a mix of all of these things, right? It's not that you necessarily have just isolated binaries or just dynamical formation or just chemically homogeneous evolution. You might, for example, have a situation where one companion evolves through chemically homogeneous evolution, being more massive, and the other companion evolves as a normal star. It's not spinning fast enough to be chemically homogeneously evolving. Or you might have a situation where you have a massive stellar binary within a globular cluster, and it's evolving as a massive stellar binary, maybe going through a channel like this isolated binary evolution through a common envelope phase, but then maybe in this particular case the binary was a little bit too wide, wouldn't have been able to merge in the edge of the universe, but fortunately it happens to be in a globular cluster, and dynamic interactions come along and help the binary to merge. Right, so you can have combinations of these things. And one of the particularly interesting ones has to do with few body isolated systems. So you can imagine having a situation where you don't just have a binary, you have a triple or a quadruple. And there are massive stars, in fact, have a binarity fraction larger than 1, meaning that typically a very massive star will have more than one companion on average. So it's more likely to be born in triple than even in a binary. So in that case, what you can form, for instance, are so-called hierarchical triple systems. You have an inner binary, and then you've got a tertiary companion orbiting around this inner binary. And in some cases, this configuration can lead to something called Lidov quasi-resonances. These are things that actually were initially discussed in the context of planetary systems and exoplanets, but they turn out to, of course, also play a role for gravitational wave sources. The basic picture is something like the following. I have an inner binary, which I'm intentionally drawing as being somewhat eccentric, and an outer binary, which is inclined relative to it at some fairly high inclination angle. Iota is, not that far away from 90 degrees, let's say. Actually, let me initially draw this as maybe not being so eccentric. So maybe this is initially a fairly circular inner binary. What you can have happen is a little bit akin to an exchange of angular momentum between the inner orbit and the outer orbit. So through interactions between inner and outer orbits, and these are the so-called Litov quasi-resonances. So basically, if you think of this configuration, in this configuration, at least all the angular momentum in the z direction basically belongs to this inner binary, because the outer binary is inclined at almost a 90-degree angle. So it's it's in the zy plane or something like that. So it has almost no angular momentum in the z direction. Now, if you exchange some angular momentum so that the outer orbit begins to tilt this way, the outer orbit now ends up with some angular momentum in the z direction, which means the inner binary has to lose angular momentum in the z direction. And the way it does that is that it stretches. It becomes more eccentric, right? Because an eccentric binary has less angular momentum in the z direction. Yes, please. Oh no, that's what I mean, right? So sorry. When I say outer binary, I really mean a third object moving around this inner binary. So that's what I mean by hierarchical triple. This outer thing has to be, in order for this thing to be stable, it has to be about sort of 5 times larger in terms of its orbital separation than the orbit of the inner binary. Otherwise, these things get very quickly unstable. But indeed, it's just a third object orbiting around this inner binary. And through this exchange of angular momentum, you can drive up cyclically the eccentricity of the inner binary. And if you drive up the eccentricity, that means that suddenly this binary, which was not able to efficiently emit gravitational waves because its orbital separation was too large, at least at periapsis, if you really drive up eccentricity like 0.999, the periapsis distance gets short enough that suddenly you can have efficient radiation of gravitational waves. Now, of course, efficient radiation of gravitational waves quickly dampens down the eccentricity, because you're radiating gravitational waves at periapsis, which is equivalent to getting a kick at periapsis. So you always return to the same periapsis point, but with less orbital energy. So the semi-major axis shrinks, but periapsis distance stays the same, and so therefore your binary becomes more circular. But that's all right, because there's going to be another cycle of these quasi-Litov resonances, and you can drive up the eccentricity again. And so you have these cycles of driving up the eccentricity of the inner binary and damping out that eccentricity, but in the process radiating energy in gravitational waves and bringing the binary closer together. And if the configuration is just right, you can end up in a situation where you drive this inner binary to merger by virtue of going through many such Litov quasi-cycles. And of course, you again have to, we can write down what the typical time scale is for these cycles, what is the typical maximum eccentricity you can reach, and so this is obviously sensitive to the choices of the binary's parameters and the triples parameters. So what are the ratios of the inner and outer orbits, what is the relative inclination between them, and so on. We, a lot of this is based on, I think, rather unfounded assumptions. For example, when people estimate how frequently you might find useful triples, by useful I mean things that can drive the inner binary to merger, people will do things like say, oh, let's assume that we're drawing the eccentricity of the inner and outer binary independently from a thermal distribution. Or let's assume that the inclination is, relative inclination is drawn uniformly, or whatever. And that may be reasonable, but we don't know, because of course, it depends on how you form this triple system in the first place, and the formation might leave its imprint, and maybe the initial conditions you need for the binary, the triple to be useful, actually never occur in nature. Or maybe they occur in nature much more often than you might think by pretending that this is somehow a, you're drawing all these angles from independent uniform distributions, right? So I think this is one of the questions here, what are the reasonable initial conditions for these things? But at least in principle, it's certainly, I think, fair to say that these kinds of behaviors can happen. And by the way, it's worth saying that, I raised earlier this point about nuclear clusters, but for example, you can actually have your hierarchical triple, the third object here, be the supermassive black hole. If you have this binary orbiting around somewhere in the sphere of influence of a massive black hole, it's that massive black hole that can be the third body in your quasi-triple and can lead the binary to become more eccentric and lead black holes to merge. It can also actually lead stars to merge, so you can have enhanced just normal stellar mergers because of the presence of this massive black hole and so on. So this is certainly one possible channel, and it also has some interesting predictions for spin-orbit misalignment angles and so on. So in the last 10 or 15 minutes, let me just mention where this might go, because of course we've now discussed a few different possible channels, and you might ask yourself, okay, so how do we learn anything? Given that we have these channels, we don't even know which one is the dominant channel, which one is the right channel. How can we learn anything? Well, I think broadly speaking, there are two approaches. One is a kind of very weakly modeled or almost model independent approach, right? You can look for just overall properties in the behavior of observed populations. So one way to do that, for example, is by looking for clusters, right? Clusters in whatever observable parameters you have. So to give you an example, think about gamma ray bursts, right? At some point, okay, people detected a few gamma ray bursts. That was very exciting, but it was hard to figure out what the channels might be. And then people noticed that there were actually two subcategories of gamma ray bursts, so-called short bursts and long bursts, but they weren't just short and long. Yes, it's true that short bursts have a typical duration of less than 2 seconds, and long gamma ray bursts have a typical duration of more than 2 seconds, but that's not the only thing that distinguishes them. Because short bursts also happen to have a much harder spectrum, typically, so a larger fraction of energy emitted at shorter wavelengths, higher frequencies, but also, for example, they were much more distributed in their host galaxy, whereas the long gamma ray bursts were found to be concentrated in the very central regions of the galaxy where you had a lot of star formation. Also, different galaxy types were responsible for them. Long gamma ray bursts were found exclusively in star-forming galaxies, actively star-forming galaxies. Short gamma ray bursts, at least a quarter of them were found in, or about a quarter of them were found in red and dead ellipticals. So you begin to see, okay, there are these two different populations here, and that starts you thinking about, okay, so maybe there are actually two different progenitors, and indeed, I think now it's quite well established, especially thanks to GW 170817, the binary star merger that was sort of the last straw in establishing this, that short gamma ray bursts come from compact object mergers, either double neutron star or neutron star black hole mergers, and long gamma ray bursts come from collapsars, a subset of core collapse supernova. So can we do something similar? Can we look for clusters in the space of observed parameters? Masses, spins, okay, any properties of the host galaxy where we happen to be able to identify a host galaxy, and so on. And this is one approach. We've been working on this, and I think have some algorithms in place for doing this kind of clustering in multidimensional space. And so we think we can, for instance, distinguish multiple subpopulations, at least in our models where we create multiple subpopulations and then run them through our clustering algorithms. We can distinguish multiple subpopulations with a few tens of events. So that's one possibility, and then you can say, okay, well, if I see, let's say that there are two different subpopulations of binary black holes, maybe that tells me that I may not know for any individual system which subpopulation it belongs to, because I always have measurement uncertainties and so on, but if I see two broad clusters, maybe that starts telling me that there might be two dominant formation channels, and I can start trying to figure out, okay, what their properties are. Or look, this formation channel typically produces, higher masses and more significant aligned spins. Maybe that's the chemically homogeneous evolution channel, right? So that's one way of going about it broadly. And of course, you can also always do, an even simpler version of this perhaps is you can focus on, just maybe one parameter and look at its distribution, infer its distribution, and say, can you learn something from it? I mean, it's just interesting anyway to figure out what is the distribution of spins, what is the distribution of masses, and whether, for example, the distribution of spins is consistent with isotropic spins or aligned spins, or what it's telling you about the spin magnitudes. The other approach is a more modeled approach where you say, okay, let's create a bunch of models. Our models definitely have some free parameters. There are some uncertainties, like we don't know what is the natal kick of black holes. We don't know how efficient the ejection of a common envelope might be. We don't know how strong the stellar winds are and how much massive stars lose in stellar winds, especially during particular stages of their evolution, like luminous blue variables. We can try to parameterize all of these uncertainties, create a large set of models, and figure out what each model tells us about the, not just, of course, the total rate of binary mergers, but also, for example, the mass distribution of binary mergers. And then we can say, okay, can we now figure out, based on our observations, which model is in fact the right one? So this is really inference akin to the kind of inference that people are doing on individual gravitational wave signals when estimating their parameters, except now you're doing inference on the whole population, and your parameters aren't the masses and spins of each binary, but they are these population parameters that govern binary evolution, like the parameters that describe the kick distribution, for example. So what do you need to do in order to make this happen? Well, the overall framework for doing this kind of inference is actually not all that different from the parameter estimation that Alan has told you about, or that Neil Cornish will tell you about next week, I guess. You can still use Bayesian methods and stochastic samplers like Markov-Chain Monte Carlo and so on, right? That part is straightforward. We understand how to do that. The difficult part is twofold. One is figuring out, of course, how to parameterize these models, right? What are the physically useful parameters on which you want to do inference? But the other one is actually computing the models. It's a little bit like the problem that you would have had with numerical relativity. If all of your waveforms for gravitational wave parameter estimation came from numerical relativity, those waveforms, one waveform might take you a month on a supercomputer to compute. And if you now want to explore a large dimensional parameter space where you might need to compute 1 million different waveforms spanning this parameter space, you say, tough luck. I don't have the resources. So people have been coming up with various surrogate models that are relatively computationally inexpensive. So one of the things you want to do is figure out a way to come up with surrogate models for the kinds of compact object binaries you might form depending on your assumptions about your astrophysical model parameters. And so that's one of the things we've been trying to do recently. Turns out it's not so trivial, but there are actually some nice machine learning tools like Gaussian process emulators that allow you to do simulations in only a few places in your parameter space, and then use those to calibrate your predictions, so you can make predictions for the mass distribution and the rate of binary black holes at a different value of the kick velocity, and a different value of the common envelope efficiency parameter, and at a different value of the parameters describing the mass loss rates due to winds. Another approach in the same vein is to ask, well, but okay, how well could you hope to measure things at all? And this again harkens back in some ways to what people have done for the gravitational wave data analysis 25 years ago. So if you look at papers, let's say from the late 80s and early 90s by people like Cutler and Flanagan or Poisson and Will, you will see that they didn't have necessarily the computational resources or the desire to run these Bayesian stochastic samplers. What they did was they used the Fisher information matrix to figure out what is the local structure of the parameter space, and therefore essentially the inverse of the Fisher information matrix is a pretty good approximation for a covariance matrix in the high signal to noise ratio regime. And so you can use this to figure out, okay, if I did get enough data and I did, let's imagine for the sake of argument, have good enough models, how well could I actually infer the parameters? So it's not a parameter estimation tool, it's a tool for figuring out how well you could do parameter estimation once you have the data and once you have the good models. And we can apply similar techniques to this kind of model-based learning about populations. And so one of our students, Jim Barrett, had written a paper recently where he has done exactly that, and we actually figured out that it's not all that hopeless. We considered something like 4 different parameters in this particular case. One can, of course, increase the number of parameters. We just started with, a number that made things non-trivial, so you don't have one parameter, but that still made things computationally manageable. So we started with 4 different parameters describing some of these uncertain quantities I described, and said, okay, if you had 1,000 detections, yes, we're being very optimistic. We're looking, to full design sensitivity advanced LIGO operating for a couple of years, but once, it's not a completely crazy number, and okay, the accuracy doesn't degrade so hugely if you go to 500 instead of 1,000 detections or whatever. How well could you measure these parameters? Because of course you have significant correlations between these parameters. And we still found that you can get them to a few percent fractional accuracy. So that's actually telling us that yes, there is hope for doing this model-based learning about astrophysics using large observational data sets, even accounting for the measurement uncertainties present in each given observation. So, future is bright. Well, at least it's bright in gravitational waves. And remember, gravitational waves are the most luminous things in the universe, so the future is bright indeed. Thanks. Yes, please.
So in gravitational scattering, I guess either of stars versus compact objects, can you affect the spin very much?
No, you don't actually affect the spins very much until you, basically you have to get quite close together, right? You can just think of sort of, the multiple moments that the spins would give you, right? And you think of the potential, your mass gives you 1 over r potential, your mass dipole gives you a 1 over r square potential, etc. So your spins end up giving you something like a 1 over r cube potential. So it's kind of the same order as your roughly as your mass quarter-pole moments. So it's not going to give you a huge effect until you get unless you get very close together, right? So of course they do have an impact during your post-Newtonian evolution. You have this precession, for example, and so that means that your spin configuration actually doesn't stay exactly the same. There are some quantities that are conserved, but in general, if you start with a binary like this, this is my orbital angular momentum and these are my spins, it doesn't mean that the spins have exactly the same configuration all the way through. Because, for example, both the spins individually and the orbital angular momentum precess around the axis set by the total angular momentum, and they precess at somewhat different rates set by the relative masses. So the exact configuration doesn't stay the same, but in general, for example, and this was something that was shown by Jeremy Schnittman in, I think, 2004, and people have confirmed this since, that you find that if you start with an isotropic configuration in a binary, let's say, then isotropic still gives you isotropic at the end of the day, whereas preferentially aligned gives you even slightly more aligned after post-Newtonian evolution. Yes, please. That's a very good question. I don't know, is the short answer. There are ideas in both ways, but I don't think we actually have an answer. We know that, it seems natural to assume that initially your stars will actually be born not just in doubles or in binaries or triples, but in sort of, 10 or 20 stars being born together in a single star formation episode because of the fragmentation of some molecular cloud. But the details of their subsequent interaction, I think people are still working on that. You might have plenty of mergers happening early on because initially your pre-main sequence stars are quite large. You might have this accretion that's actually getting your lighter objects to accrete more mass and kind of bulk up to be closer in size to the more massive objects. But I think there are lots of uncertainties there, and people are even not entirely sure about the very fragmentation of the molecular cloud, how efficient it is, how much feedback there is from the first episodes of star formation and collapse, which then heats up the rest of the cloud and prevents, let's say, larger sized chunks of matter from collapsing because of Jean's mass arguments. Thank you.